Hi everyone. So I'm Claudio, last speaker of today. Um, Let me try to start it. I'll try to stay within 10 minutes. I'll give a brief overview of the work. I've been working for the past few months with Emin, a friend from KU Leuven in Belgium. The idea behind this work started with early collaboration with Martin Benedict and Frans Holzman, where they described co-simulation scenarios that had particular preferences to specific orders, and this led us to ask, okay, but where do these preferences come from? And this is where we started this work. So I'm going to give a small running example. To start, this is a double mass spring damper. It's a favorite of ours because it's a common system in practice. The joints that we study, so that we split the system into two FMUs, and they are connected by a common mechanical coupling. So where we have a particular effort variable and a flow variable. So this is a power connection. So it's a representative symbol, even though it's very simple, and even though we also can get an analytical solution for it, which makes it very useful to test new co-simulation algorithms. So if you look at this example with two FMUs, and let's assume the FMUs implement this interface, so a simple three functions, two-step, set input to a particular value and get output to get a particular value. There can at least be two possible master algorithms to solve this. One of them will step FMU1, the MSD1, the first mass spring damper. It will step it first, get its outputs, and then set the inputs to the second FMU, and then it will step the second FMU. What happens here is that the first FMU, because it's the first one to step, it has from a time t to a time t plus h, it has to guess what would be the input behavior in the interval from t to t plus h. And it has no access to the value of the input at t plus h because it has to step first, therefore it has to extrapolate. So this correlates with what Simon was presenting before. On the other hand, the second FMU to go forward is the lucky one because that FMU will have access to the input at the time t plus h because the other FMU has already stepped into that time, and so it can do an interpolation. And generally, doing interpolations is better than doing extrapolations. We would like to do as many interpolations as possible, but of course, from this scenario, you cannot have the two FMUs doing interpolations without getting into an algebraic loop. So avoiding that, you can also you have to choose between these two algorithms, choosing whether this FMU goes first and extrapolates, or choosing whether this FMU goes first and extrapolates. So this is the essence of the problem we're trying to solve. Pick what is the best master algorithm, and of course, is this a problem at all? Yes, it is very easy to see that this is a problem because if we get the analytical solution, if we focus on a particular variable, for instance, the state variable, the velocity of the FMU, we can compare it with the analytical solution, and we can see for each algorithm we can plot this error, and we can see that indeed this one is very bad because it has a much higher error than this order here. This is good, but in practice we don't have access to analytical solutions. So this prompts two questions. One of them is there a best order? Is it fixed for a given co-simulation scenario with a certain underlying system? Is there a single best order, or does it change over time? You can see here that there's certain times where actually this order is performing better than the other one. But on average, most of the time, this order is better than this one. So does it change over time? These are the first questions. How do you figure out what the best order is? So to address the first question, it's fairly easy by manipulating the parameters of the system. By changing the stiffness coefficients, the damping coefficients, and so on of this to a very simple system, we can already get some complex behavior on the error. And you can see here that there is no clear, at least up to time 2.5 or so, there's no clear winner as to what the best order is. they seem to change roles over time, and then at some point it actually you clearly see that this one gets to be the winner because it has the lowest error over time. So this answers our first question. We need an adaptive master algorithm, and a master algorithm that will at any point pick this order or this order depending on some estimate of the error it's making. And as I said before, we don't have an access in a real co-simulation. We don't have access to the analytical solution, so we can't just make this plot and solve the problem. So we need to figure out how to find the best order. And for that, there's 2 steps involved. One is we need to figure out, find an estimator, find a formula that estimates the state error in all possible orders so that we can compare which order is giving at any point in time is giving the lowest error possible, and we can switch to that order. So this is the 2 steps. First, let's get this state estimator. What we did so far was said, also borrowed from an idea that that's done in a state of the art. We'll check. First, we made an assumptions, and this work, again, I didn't list a long list of authors at the beginning, but these assumptions come from discussions with Casper, with Kenneth, with Peter, and so on. But we were making an assumption that errors at inputs translate to errors at the state. And this is fairly common in co-simulation, that the main factor in the error is caused by the inputs of the FMU being extrapolated or interpolated. And we could see this for particular configurations of the system. This is clear. So in this case, we see the input error indeed seems to be an indicator on a particular order. It seems to be an estimator of the error being caused in the error. But again, for other configurations, it is not so clear. You can't really make this conclusion evident. So we have a problem, but for now, we will just state this hypothesis is true. We will assume this hypothesis. And so then we can easily build an estimator for the input error, which is available in any co-simulation. And this estimation goes by, first, if we are in a particular order, let's pick this order, then what will happen is S1 will step first, and we'll have to do an extrapolation. There's nothing you can do about that. But then after we finished moving the second FMU to the time th, we will get a value back for that input. So we can actually compare, okay, what was your extrapolation with the actual input that you got at the end of the co-simulation step? And this difference is an indicator of the error. And this is here it means this is the error incurred by staying in the order in this particular master algorithm. That's the error I'm making right now. So what would be the error that the opposite order is making? Well, in that case, it's easy. We just repeat the same computation, mimicking an extrapolation of S2 for its inputs. Because we know S2 is doing interpolation, that's for sure. But we can simulate an extrapolation for S2 and we can compare that result. So now we have part of a solution, but also a new problem. We have 2 inputs, and we can estimate the error being made at these 2 inputs, and we can estimate the error being made at this guy's inputs. So which one is more important? Which of the 2 errors are more important? And this is where it's very useful to collaborate with mechanical engineers, because they'll say, well, you just need to convert them into a force. So you can compare 2 forces. Instead of using fancy mathematical norms, we use a physically motivated measure. And this is, we can get the system parameters representing the force. The coupling force here is a function of these 2 inputs. And these system parameters give you what this function is. So this solves the problem of comparing these 2 quantities and giving us a meaningful comparison to define which orders should we switch. So some results here, what we see is, this is the measure taken from the previous slide. You can see here, it says here at the beginning that the first order, the blue one, is the best one, because the orange order is much higher. Right? And then at some point there's a point where they are equivalent and so on. But most of the time the blue order is the best, and indeed this corresponds to the analytical solution that we have. So this is a good indicator. It's not perfect. You can see some discrepancies here, but overall it's a good indicator. Things are a little bit better on this side when it comes to different. So even though we assumed hypothesis 1, and this showed that hypothesis 1 was not entirely good, Still, this approximation of the input error still shows good results for this nasty system configuration. So you can still see that it usually the orange one is the best one at the beginning, and then it becomes worse. That's about it. The summary of the algorithm, essentially, if I am in order in one particular master algorithm co-simulation step, I compute it. At the end, I will compare the two estimates for the inputs. If the current one, the current error I'm making in this order is much higher than the hypothetical error, then I switch, and vice versa. So for the next steps, we will improve. Min is working on improving the state error estimator, particularly taking into account the Jacobian of the system. This should improve our hypothesis one to make it more meaningful. We are planning on integrating this algorithm, figuring out how to integrate this adaptive algorithm into Maestro V2. Emin is also developing a more complicated case study with a CAM follower. And of course, I would like to see Simon and Maurizio work on trying to validate this adaptive master algorithm. And that's all.